Jupiter just got a surprising update, not because it changed, but because our measurements finally became far more accurate. For decades, scientists relied on Jupiter-size estimates from older missions like Voyager and Pioneer during the 1970s era. Now NASA's Juno spacecraft has delivered new data showing Jupiter is slightly smaller and flatter than previously believed. This doesn't mean Jupiter shrank. It means we have corrected decades of imperfect measurement techniques and assumptions. Juno orbits extremely close to Jupiter, allowing scientists to study the planet with precision never possible before. One key tool is Juno's radio communication system, which becomes a scientific instrument during each orbit. As Juno sends radio signals back to Earth, the signals travel through Jupiter's thick atmosphere on their way. Jupiter's atmosphere bends these radio signals slightly, changing their frequency in measurable and predictable ways. Scientists call this effect radio occultation, and it helps map how the atmosphere behaves at different depths. By measuring the bending, researchers can calculate atmospheric density, pressure, and even subtle structural variations. But Jupiter is not a calm planet. Its winds are among the most powerful storms in the solar system. These winds distort the planet's shape, especially near the equator, where rotational speed in storms are strongest. Older missions could not fully account for wind-driven deformation when calculating Jupiter's true physical dimensions. Juno's modern instruments allowed scientists to include wind effects into the shape calculation more accurately. When they corrected for wind influence, Jupiter's true radius values became slightly smaller than earlier numbers. The new results show Jupiter's polar radius is about 12 kilometers smaller than previously estimated. That may sound tiny compared to Jupiter's enormous size, but scientifically, it's a major improvement in precision. Even the equatorial radius was updated, measuring roughly 4 kilometers smaller than older accepted values. Together, these updates confirm Jupiter is slightly more flattened than earlier models predicted for decades. This flattening is expected because Jupiter spins rapidly, completing one full rotation in under 10 hours. That fast spin creates a strong, bulging effect at the equator and compression near the poles. However, accurate measurements depend on separating rotation effects from atmospheric wind distortions and pressure layers. Juno's data allowed researchers to refine the reference surface used to define Jupiter's actual planetary shape. This gives scientists a clearer understanding of where Jupiter's visible atmosphere ends and deeper structure begins. Even small changes in radius affect calculations of Jupiter's volume, density distribution, and gravitational models. Those factors matter because Jupiter's gravity reveals clues about what is happening deep inside the planet. Scientists use Jupiter's gravity field to study its interior layers, including the possible size of its core. A slightly smaller radius changes how models interpret the mass distribution beneath Jupiter's thick atmosphere. This helps researchers refine theories about whether Jupiter has a solid core or a diffuse, diluted one. Understanding Jupiter's interior also explains how the planet formed during the early chaotic days of our solar system. Jupiter likely formed by rapidly gathering gas and dust, growing into a giant before the solar nebula disappeared. Precise shape data improves simulations of that formation process and helps confirm which model best fits reality. It also helps explain Jupiter's heat, magnetic field strength, and the strange behavior of its deep atmospheric layers. Juno has already discovered that Jupiter's storms extend far deeper than scientists expected before the mission began. It also revealed that Jupiter's famous jet streams are not shallow winds, but deep dynamic structures. These winds influence the planet's overall shape, making measurement far more complicated than a simple sphere. This is why Juno's updated calculations are so important for planetary science and future exploration missions. The study behind this discovery was published by Caspi and colleagues in Nature Astronomy in 2026. The findings were also reported through popular science sources like Live Science, spreading the update worldwide. The most fascinating part is that Jupiter didn't physically change, only the precision of our instruments did. This shows how science constantly improves, correcting old numbers as technology evolves and knowledge expands. Earlier missions did incredible work, but they lack the close orbital measurements that Juno now provides. Juno's orbit allows repeated passes, collecting large amounts of consistent data over long periods of time. That long-term data improves confidence and reduces error, producing measurements far closer to Jupiter's true shape. This refined Jupiter model becomes the new baseline for studying every future observation of the planet. It also helps scientists compare Jupiter with Saturn, Uranus, and Neptune, identifying patterns in gas giant evolution. Gas giants may look similar, but their internal structures and formation histories can be very different. Jupiter is a key reference point because it is the largest and most massive planet in our solar system. Improving Jupiter's measurements improves how we interpret measurements of all other giant planets and exoplanets. Many exoplanets are gas giants too, and their observed size depends on how accurately we model atmospheric distortion. If Jupiter's radius needed adjustment, then distant worlds measured by telescopes may need refined modeling as well. Scientists often use Jupiter as a calibration tool, so updating its shape improves astrophysical calculations beyond our system. Even a few kilometers difference can change equations used in planetary science and interior structure predictions. Jupiter's size affects how we calculate its gravitational pull, its pressure layers, and how deep storms might reach. It also helps scientists better understand Jupiter's intense magnetic field and how it interacts with charged particles. Jupiter's magnetic environment creates radiation belts so powerful they can damage spacecraft electronics without protection. Juno itself was designed with heavy shielding because Jupiter's environment is one of the harshest in space. Despite these dangers, Juno continues to provide groundbreaking data with each orbit around the massive planet. This discovery proves that even well-studied planets still hold secrets waiting for better technology to reveal. Jupiter remains a laboratory for understanding physics, storms, gravity, and planetary evolution on a massive scale. And the more accurately we measure Jupiter, the closer we get to understanding how planetary systems truly form. So Jupiter didn't shrink, but our knowledge expanded, giving humanity a clearer picture of the solar system's giant king. This is the power of missions like Juno, not changing the universe, but changing what we thought we knew.